All right, let's work. All right, happy Friday. Let's see. So MP6 extra credit is due tonight. As you well know by now, it's our little implementation of a KD tree. And my affection for this MP comes from the fact that, yes, it's true, you're implementing a tree, but it's a smashed tree, all of which exists in an array. So this is, I want you to just be kind of hyper aware of the fact that, yes, you are still implementing a tree, but underneath that implementation is just an old array, just like the arrays you've used since you were a kindergarten programmer. Could you do me a favor and take this pile over to that chair? Thank you. Okay. You guys didn't mean to distract me, but I'm just distracted. It's Friday. Okay, let's see. In terms of exam grading, we decided sort of at the last minute to add some test cases that are alternative test cases to the exam grading, and what they will do for you is they will make it more likely that you get partial credit. So they are additional kind of easier test cases, and we're grading on a disjunction, or if you get points if you get one or the other of these test cases correct. Now, the cost of it is we're doing all the grading runs again. So you still don't have scores for exams 3 or 4, but we're working on it, and exam 5 will follow shortly thereafter. Sometime this weekend, I'll send out the final policy statement on exam 7, which will be that retake exam. Some of the questions on the board are what to do if you're totally happy with all your exam scores. What should you do? And we'll come up with something that's fair there, fair or reasonable, or both. Okay, so let's talk about our very last implementation of dictionaries. I don't know about you, but I am tired of dictionaries. We only have a month left, but we still have a bunch, actually, of incredible abstract data types to talk about. 3 in particular. And I feel like we could spend a whole semester on those last 3 abstract data types. So I am really ready to get done with hashing here. All right, so we've got this implementation of a dictionary. That is, the responsibility for implementing it is limited to functions insert, remove, and find. The particular interface that you're going to use for those functions is an associative array. Now, we talked about this hash table in a fair amount of detail last time. In particular, we noted that hash table will always have an array. And when I say array here, I mean a linear structure with indices. It might be called a vector. It might be called a dynamic array. There might be some other language or a table. There might be some other language that calls it something different. When I say array here, I mean sort of array in the general classic sense. Indices, locations, random access, or constant time access to the locations within. Item number 2 is a hash function. And we talked last time about characteristics that a good hash function has. It is computable in constant time. It is deterministic. That is, we don't flip a coin to decide where your data goes in the structure. And it is, it satisfies SUHA, meaning that it spreads the data out over the table, spreads the data out uniformly over the table. And there's a probabilistic description of it, but we won't talk about that here. We saw an example of a perfect hash function and noted that if your key space is small, you can design a perfect hash function. But that's pretty artificial. That's pretty artificial because a lot of times our key space is so large relative to our table size that there are so many different subsets that we can draw from our key space that we are very, very likely to get a subset for which more than one of our keys, say call this key 1, call this key 2, hash to the same cell, okay? If you're thinking about this in the terms of hash functions, we say that it's very difficult. For a large key space, it's impossible to come up with a hash function that is one-to-one. And in our vernacular of the trade, we call this sort of violation of one-to-one-edness a collision. So a collision occurs when there exists K1 and K2, which are not the same keys, with H of K1 the same as H of K2. Okay, so they map to the same spot. Today, we're going to spend all day talking about what to do in that case. That is, we're going to spend the day talking about collision resolution strategies. Okay? Now, you can kind of imagine what the setup is, right? You've got two keys, they want to go in the same cell. It's not like you can say, okay, you guys go in that cell and decide who stays, and you're staying in until you come to an agreement, right? This is not conflict resolution. This is math and data. It's collision resolution. So we programmatically have to decide what we're going to do with those keys in code. Okay, so I scratched this out. There are two different strategies that one might take, or two different kinds of strategies that one might take. The first one is called open hashing. It's an example of open hashing, and when we say open hashing, we mean that you don't actually have to fit all your data in the table. So all the data doesn't have to fit in the table itself. Okay, it's open. The table is open. All right, so what's our strategy here? Well, we just let our data collide. That is, if two keys map to the same cell, we just let them live in the same cell. Now, there are a couple different ways of doing that. The classic one that we're going to talk about is separate chaining. And all we do is we build a linked list out of that data. That's it. Okay? All right, so let's do our little example here. Here's our keys, our set of keys. These things are keys. And here's our hash function. The key mod 7. Ooh, we're complex here today. The way we're going to keep track of our data is simply to make a linked list in each of these. So each of these is actually a node pointer, okay? Classically, that's true. All right, so let's process our keys. First key we get is 16. Where does it go? Where does it hash? To value 2, good job. So all we do is we insert 16 into the chain administered by cell 2, okay? All right, and then we get an 8. Where should we put 8? How about 1? Good. So 8 goes here. 4, even I can do that one. 4 goes here. Things are going to get more interesting in a second. 13, I think 13 goes here, yeah? Where does 29 go? Oh, 29 goes 1. Okay, into 1. So we have a choice to make. Should we put 29 out here, or should we put 29 there? Raise your hand if you prefer to put 29 over here. Okay, and raise your hand if you prefer to put 29 here. Okay, I'm going to put 29 there, and let me talk about why. So close your eyes for just a second. Close your eyes. I don't want you to think algorithmically here, okay? So close your eyes. Yeah, don't look, don't look. Oops. Ugh. There, I inserted 29 in the front, okay? And the reason I didn't want you to look is because I wasn't doing it algorithmically. It was just trying to sketch it. Okay, so the reason I put 29 in first is because I don't want to have to find the end of the list. Now, I think those of you who suggested that I put it at the end, you're kind of thinking, oh, maybe we should keep these in sorted order, right? But you know what? Sorting your data inside of a linked list, it doesn't really help you much, right? You still have to walk the list looking for the value. You don't gain the binary search there, okay? Any question about that? So we're just going to chunk it in the front because there's no reason not to. Any question? Is it good? Okay, let's finish adding these in. So we're going to put 11 into the chain at cell 4. So I'm going to do that, you know, I'm not really moving data. I'm not really moving data around here, okay? Even though it looks like it, I just want the picture to look right. I'm not really moving data, okay? And then where does 22 go? Yeah, 22 goes in 1. Oh, brother. There, that's better. All right, any questions about inserting into this structure? All right, so let's talk about find on this structure. So find, let's say we want to do a find for 4. What's our algorithm for that? We're going to hash 4, and we get 4. So we go to the chain for 4, and we go off in search of it. Are you 4? No. Are you 4? Yes. And we return the value, okay? Oh, I guess it's worth saying that, as in many of our examples, you can assume that these are really key value pairs. So this is 13 plus any data that we have associated with 13 as its value, okay? All right, any question about insert or find? Imagine for just a second, take 15 seconds and think about how remove might work. Did you do it? Anybody want to describe it? How does remove work? Remove of 16? Yeah? Tell me real quick. Yeah, very good. So it's just a find and then a removal once you find it. Yes? Yeah, maybe it should be doubly linked. That would be fine. There's no real reason not to, except that it uses more storage. Are you worried because it's easier to remove things when it's a doubly linked list? Yeah, okay, whatever. We could get, you know, whatever, that's fine. Since you're walking forward, you can always stop one early too. So, sure. I think there's another question that follows right on the heels. No. So when somebody opens the can and says, well, could we use a AA linked list here? What else do you think you might be able to use here? Yeah? An array, maybe an array. How about something else? Yeah? A binary tree. Oh, like a binary search tree maybe even, right? So that you wouldn't have to necessarily look at all of your data. Yes, there's a point at which I'm going to say, no, those are all bad ideas in just a bit. Not now. I mean, they aren't bad ideas, of course. That's a perfectly reasonable thing to do. We're looking at only the classic structure, but I want to talk later about why we're not going to use binary search trees, in particular in this context. And it has to do with the reason we're not going to worry about whether or not these things are sorted. Whoa, that's a teaser. Okay, so let's talk about running times, in particular for insert. What could go wrong? What could go wrong with insert? Yeah? All the keys hashed to the same place. Does that hurt us on insert? No, it was a bit of a trick question, right? It was a bit of a trick question. Insert, we've got it set up so that if you have a constant time hash function, you're always just going to insert in the front of this thing, okay? So for insert, you don't really care. But now I'll take your answer for remove and find. Anything that requires any kind of searching is going to induce bad behavior if your keys and their relationship to the hash function are such that you have a bunch of things mapping to the same value. Now, for example, imagine that your keys are scores in football games, American football games. I apologize for the cultural reference here, okay? American football is a sport played on a 100-yard field, and one of the most common scoring mechanisms gives you 7 points with pretty high probability, okay? So in that case, you're going to have your multiples of 7 frequently mapping to the same place in this particular setup, right? And so that would be bad news. And in fact, the very worst thing that could happen would be that everything maps to the same spot. Okay? Now, here's what Suha gets you. Here's where Suha comes into play. We imagine that the people who have created the hash function for us to use in our particular context have created a hash function that basically takes any key and chooses a random spot for it in the table. In that case, and it's a probabilistic argument, but nonetheless, what we expect is that the number of elements in each of these cells or each of these lists is the total number of elements up here in our sample, in our set of keys, not our key space, but the set that we're using, divided by our table size. Okay? Now that's an expected number, but it's still, you know, we assume that it's true in a given hash function. Okay, any question about that? Yeah? There, oh, right. Oh, did you all hear that? Isn't that still big O of n? Well, let's take a closer look at this. Let's take a closer look. You're right. This is our data size. It's growing. It always reflects our data size. It's the parameter to the problem. This is our table size. Is it constant? No. Who controls it? Who controls what the table size is? We do. We control the table size. So this is a perfect opportunity for me to introduce to you a new term. We call the fraction of elements in each cell the load factor of a hash table. So a hash table load factor is usually designated by alpha, sometimes by lambda, but for our class we're going to use alpha every time. And it is our data size over our table size. Okay, and it just reflects how full is our table. Okay, something key to point out here is that for our current scenario, alpha can be greater than 1, right? For separate chaining, we could put hundreds and hundreds and hundreds of things in this table, and that would be fine. We just have really long chains, okay? But we don't care, okay? So that's open hashing. Open hashing allows you to put more data in than your table size even, all right? Okay, so are there any questions? So I'm going to kind of leave our discussion of load factor and this running time there. So it's true, we control this n, and in fact, if we control this n, we can make it so that that thing is fixed. But that's kind of foreshadowing. I want to talk about that after I talk about this next collision resolution strategy, okay? All right, any other questions? Any questions about separate chaining? Okay? All right. So another collision handling mechanism is referred to oftentimes as probe-based hashing. It's an example of closed hashing in that your data must fit in the table, okay? So your data must fit in the table. All right, so here's how it goes. I'm going to use the same hash function, and the beginning of it is just to try to hash it. 16 mod 7 is 2. If there's space, I'm just going to put it in the table, okay? 8 mod 7 is 1, no problem. I'm going to put it where it belongs. 4 mod 7 is 4, goes there. 13 mod 7 is 6, no problem. Boy, this is a boring technique, right? Except that now 29 mod 7 is 1. So here's what we do. We try to hash into its spot. If we fail, that is, if the spot is already full, we just look in the next slot. If it's already full, we go to the next slot. We plunk it in, okay, so when we find an empty slot. Any question about that? Yeah? Yeah, so let me point out the problem with this first. I have yes, that will come next. It's a little different than you suggest, but let me show you, illustrate some of the problems with this first. All right, any questions about it, first of all? Okay, so this mechanism, this notation for the search is referred to as, or this particular mechanism is referred to as linear probing. And that's the case where we just look to the next one, then look to the next one, then just look to the next one. That's the linear part. We're going one by one down the line. And the notation we use is to take the original hash value plus one more every iteration of this thing. So it's really hard and really boring to do reasonable size examples, reasonable sized examples on the screen. So I want to show you an applet. And by that, I really mean an applet, which is quite annoying because the only device in my life on which I can run Java, apparently, is my brand new MacBook, which doesn't talk to anything else easily. So today, I don't like Java and I don't like Apple. Cancel. This is the moment. Okay. All right, so this is a hash table that contains, of size 100, it contains 100 cells. And what I want to do for you is to, first of all, I want to reset, oh, I don't know if I want to reset the page. It's paused. Close your eyes and your ears for just a second. Oh, no, it's going to take too long. I'm going to reload the page. Hold on. This was worth it, believe me. Oh, come on. Oh, no. They promised me. They said, if you get a new MacBook, you'll never see the pinwheel again. I hate them all. Illinois Net. Okay, stop. Oh. Okay. Oh. Boy, this is getting, it's like getting more important every second that this be worth it, right? Oh, the pressure. Why? No, I know it doesn't work in any other browsers. Yeah? Yeah, that, I don't like that applet. No. Yes, why, yes, I do want to run it. Okay. Setup. Change. You can tell how old this demo is. So I have this particular set of demos that I like for different reasons. You know, someday after I'm gone, somebody will have to re-implement all of these things because they really are, I think they really are pretty good. Okay. So here's what I want to do. Oops. I want to do it like this. You ready? Oh. There we go. Oh, this is perfect. Okay, this is even better than last. Are you ready? So we're just going to be hashing some values into this table. Oh. Okay. All right, so I heard somebody whisper, it's too fast, right at the start. And then I think we all collectively agree that it was not too fast at the end. That if this were the hash table into which we're trying to hash, you know, you'd be like, we're not using that one. Okay, so here's what I want you to do. We have a load factor right here. That 100% is the load factor for this table. We just filled it up. And what I want you to do is kind of based on the sound of this. The sound is a successful insertion into the structure. So based on the sound of this, I want you to estimate, I want you to tell me the point at which you think this structure is just not worth anything to us anymore, okay? Now, and then to jot down the load factor at that moment, okay? So we're going to run it again. You're going to watch when you say, whoa, this is too slow now. I want you to write down the load factor at that moment, okay? Ready? Here we go. Okay. Dun, 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 dun. Anybody still happy with this? Okay. So raise your hand if your load factor is less than, well, somebody tell me a load factor that they chose. What load factor did you write down? 41%. So raise your hand if your load factor is actually lower than 41%, the tolerance you, okay, so I think you're like, you guys are the most impatient in the class, okay? But notice there's only a couple of them. So raise your hand if the number you jotted down was 50 or less. You can raise your hands. Yours was less, so yeah. Okay, so 50 or less, and now 75 or less. Keep your hands up. 75 or less. Okay, put your hands down. Raise your hand if the number that you chose was 80 or higher. Okay, only a few. All right, so what I want is the number of people who are not somewhere between 50 and 75. The number of people who are not somewhere between 50 and 75. Okay, so that's pretty sparse. So I think actually between 50 and 75 is kind of a reasonable number, yeah? If I said, okay, look, we're going to let our table fill to 60% full, you'd kind of be okay with that, yeah? Aside from the few impatient people. Yeah, okay. Well, there's an analytical bound on this, assuming Suha and pretty independent of probe-based strategies, that basically says when a hash table gets over 2/3 full, you kind of punt and you go, okay, this is not my favorite hash table anymore. We need to change something. So when you think about hash tables as implementations of dictionaries, yes, they are arrays, but they are not in any sense full arrays. They are at most 60% full arrays, okay? At most, you know, sometimes we say 2/3. The analytical bound depends a little bit more on the particular hash function that you choose, or the collision strategy that you choose. Okay, any question about that? There's one more thing that I want you to observe. But we never had a pause function here, or pause button. Options. No. Oh, I love the sound. There's no pause. Stop. Okay, never mind. That was about 80. I got kind of tired of it at 80 this time. Okay. Yeah, we're not going to see this. Okay. Bye. Bye-bye. Okay. Wait. My other thing. Okay. All right. So, all right, so I want to illustrate a particular problem with this probe-based hashing, part of which was illustrated in those long waits and results in this analytical empirical, decision that, boy, once the table got too full, we got tired of waiting. All right. There's this problem is called primary clustering. Now, here's what happens. Suppose that I've got that many keys hashed into a chunk, okay? And, maybe I've got a few more hashed into this chunk, and there's a single cell between them, and maybe a couple cells here, and then a chunk. What I want to know from you is an estimate for the probability that you hash into that chunk under Suha. So assuming you're equally likely to hash anywhere, what's the probability you hash into that chunk? You think? Looks like about a fourth or a fifth. Okay, I'm going with 22%, okay? So the likelihood of hashing in here is about, we'll do a fifth, okay? Now think about what the result of that is. If you hash into this chunk, and it happens with not insignificant probability, you wait all this time, your data goes into here, and it creates an even bigger chunk, right? Now what's the probability of hashing into that? Yeah, it's about 40%, or so let's say 2/5, okay? So just by taking something that's kind of likely, that was the most likely chunk, we created an even bigger chunk. It's like a black hole, right? It sucks in, it becomes the most likely cluster that we hash into. And if we hash into that cluster, we have to wait a long time because it's a big cluster. This is the problem of primary clustering. Okay, so the description is we are likely to hash into large clusters of keys, and doing so increases the size of the clusters significantly, thereby in making us more likely to hash into these big clusters. There's like this circular thing going on. We're likely to hash into large clusters of keys, and doing so creates even larger clusters. Now, this happens because we're always growing a cluster. We're always growing a cluster by one, and those new keys serve as glue between the clusters. So our remedy for this is, and this gets back to an alternative strategy for finding an empty cell. Our alternative to this is to, instead of taking a single step and looking for an empty slot, it's to take a randomly sized step in the table and look for an empty spot. And the key observation is that for different keys, we're going to have different random sized steps. So we're not trotting the same path based on the original hash value. Now, how do we get a step size? How would you think we would get a step size? Yeah? Some random number between 1 and the size of the table, say. Well, what could give us that? What gives us kind of random numbers? a random number generator? Sure. This is the way you should think of hash functions. You should think of hash functions as, if Suha is true, they are essentially a random number generator on your key space. Okay, so we are going to use another hash function to generate a step size in our table. Okay, any question about that? This mechanism is called double hashing for that reason. Okay, so create a probe based on a random step size. Yeah? It doesn't, because the initial hash might cause a collision, but then the second probe is going to be in a different place than the second probe was the first time. Okay? So you're not always walking on the same stepping stones. You're guaranteeing that the path of stepping stones you're taking is a different path. Okay, does that make sense? Okay. Okay, so how does this work? Well, this time, when we hash to a new value, we have a random or a hash function generated step size. So the mechanism is similar. We have an original hash, h1, and in this case, it's going to be the same as before. So h1 of k of the key is k mod 7. But in this case, h2 of k is, oh, I forgot what I used. I'll make something up. I'm going to use 5 minus h1 of k mod 5. I think that works okay. So hash it. If that doesn't work, you know, change its parity a little bit and take it mod 5. Okay, we'll try it. We'll see what happens. Okay, so how does this work? For the first few of them, when there are no collisions, they just get hashed to their values. I think you're kind of tired of this, so I'm going to do it pretty quickly. So 16, again, maps to 2, 8 maps to 1, 4 maps to 4, 13 maps to 6, and now life gets interesting. 29 originally hashes to 1, but now h2 of k is 4, so our step size is going to be 4 in this case. So we're going to go 1, 2, 3, 4. So we're going to go here. And oh, look, it fits. Okay? Any question about it? All right. All right, let's do the next one. 11 hashes here. And this time it's 5 minus 4 mod 5, or 1. And so this one, so 11 just hashes normally, right? 11 is going to hash here. Any question about that? Yeah? So the question is about the two moduluses. Moduli, I don't know, the mod 7 and the mod 5. The mod 7 is because the table size, and it is definitely prime for a reason. Okay, we want, if, you know, there's a little bit of a proof here that I know you all could handle, but I don't ever do, I don't know why, that if you have a prime table size and you take values, random values, mod that table size, in this probing scheme, you'll eventually hit every possible value. So the 7 is deliberately prime, and it represents the table size. 5, relatively prime to that. Yes, if it weren't, it might create a cycle, right? You might get a cycle, and so it also has to be relatively prime to the table size. Okay? All right, yeah? So double hashing, because of this sort of random assumption on the values and our key choice of these prime numbers, double hashing will always find you a spot. It's not going to be worse because linear probing is as bad as it gets if you don't try to be nefarious. But if you try to be nefarious, you can be nefarious overall, right? You can always make this bad for sure. But there is a kind of hashing that creates infeasibilities. It's called quadratic hashing that says the step size changes from 1 to 4 to 9 to 16 to 25. Even though, so that can enter a cycle regardless. So I'm going to leave the number theory on this for a later course, but I think just this kind of high-level understanding that, you know, these issues can come into play is important, okay, is good. All right, so let's take a look at some analyses for just a second. I've got a page, okay? This is a page that summarizes the running times for everything. Don't look at it. Wait, don't look at those formulas. Certainly do not memorize these formulas, okay? A few of them you can get. In separate chaining, if you're looking for something, you have a cost of 1 plus possibly the cost of going down the chain, right, where this is the expected chain length. So this one makes sense. Successful means if it's in the chain, you expect to go about halfway down the chain, okay? Yeah? Okay. The other ones, though, don't look at the formulas. Well, look at them to observe the following. As the load factor increases, they increase. Okay, so as the load factor increases, they go to infinity. In fact, the graphs of all of those things look like this. The wait times, so here's linear probing. The wait times here were what you were listening to in that applet. And I believe you gave me a value probably around there, which indicated that you were not willing to wait beyond something like that. Maybe some of you gave me this value here because you're impatient, okay? But this graph tells you how long you're waiting, it implies how long you're waiting in between each of the probes, okay? Now, let's see. This one is the worst one. This unsuccessful search here is the worst one, right? This one is a little bit better, and for double hashing, look, these are yet better. Those wait times are lower, okay? But you can kind of see. So the punchline for next time, or the teaser for next time, is to say, well, how do we control that load factor? How do we make sure that we never have a table that's very full? Okay? And that's it. It's Friday. Goodbye.
Test, test, test. Check one, check two, check one, check two. Check, check, check. Check one. Check, check, check.